All right, let's try implicit differentiation with x times y equals 1. What does that graph look like? Well, you could solve it in your head to get y equals 1 over x, which looks like this. What's the name of that shape? That's a hyperbola. It's one of the classic standard hyperbolas. What's its derivative? Well, again, you could say y equals 1 over x, and then take the derivative using the power rule. That needs the power rule for x to the negative 1, which we actually haven't proved at this point in the textbook, but this is where we'll see how that ends up working. So what is the derivative? dy over dx. So we'll take the derivative on both sides, y times x there, derivative with respect to x of 1. This side is just going to be 0, derivative of a constant. This side is complicated because x depends on x and y depends on x, so I need the product rule. So what is the product rule? It's usually this derivative times the original here plus this original times the derivative here. So we'll say derivative with respect to x of x times y, and then just plain x here, and then the derivative with respect to x of y equals 0, so that part is just 0. And now let's simplify this. What's the derivative? The derivative of x with respect to x, that's just 1. Y stays the same, this is x. And then what's the derivative of y with respect to x? That's just dy dx. So now the calculus is done. Just solve it from an algebra perspective. So I would subtract y from both sides, and then I end up with x times that, so then I'd divide the whole thing by x. So I'm going to get dy over dx equals negative y over x, which seems familiar, right? Didn't we just get something about dy over dx equals this over that? But over here, it was x over y, and now it's y over x. So they're flipped. So you could go program scratch to do that, and hopefully it would trace out a hyperbola. One more thing to think about. We know the unit circle is x squared plus y squared equals 1. What happens if you're not squaring it? What if you're cubing it, for example, or a fourth power? So we could try x to the fourth plus y to the fourth equals 1. You could say to the fourth, it doesn't really matter. So this is a circle. This is a circle, but it turns out it's kind of straight-ish for a while and then has a corner, and not a sharp corner, but a kind of rounded corner. And these are called fat circles. If I can try it for squaring and fourth powering, can I try it for cubing? It turns out you can, but it's nice to put in absolute values there. So basically anything with a power higher than 2 is a fat circle. So this is still it's kind of bigger than a plane circle, but not as squared off as fourth power. If I did absolute value of x to the p plus absolute value of y to the p equals 1 to the p, you could interpolate between any of those. So we know that p equals, well, we know what happens at p equals 2 and 4 and 3. What happens at p equals 1? You actually end up getting a square diamond. At p equals 2, you get a circle like that. We saw what happens with 3 and 4. For p huge, basically infinity, you get a totally squared off square. So that's kind of fun. And you can even do p less than 1, and you get sort of a star shape like that. So in addition to drawing fun shapes, these fat circles are also called superellipse. If you put coefficients there, people have used them to design modern-looking tables and furniture, and even traffic circles, kind of, not the part that people drive on, but like a sculpture's platform in the middle of a traffic circle. But they're also useful in machine learning, especially p equals 1, 2, and less than 1, to talk about penalizing for being off in our predictions, kind of like the sum of squares. You can do sum of absolute values, or even sum of things that are taken to a square root or something, and that's a way to get better and better machine learning models. So it's fun for furniture, it's fun for machine learning, it's just all around fun.